So at the end of class on Thursday, we were talking about heating curves and drawing some heating curves. And we ended with this problem where we have this new unknown substance, dibromomethane, and we want to sketch a heating curve based on just the data that you're given, the melting point and the boiling point. So did anybody try this yet? Okay. Take a couple minutes and give it a try. So you're going to draw the axes, maybe go back and look what a heating curve looks like. In this case, we're going from minus 100 degrees C to 120, so you can label your units accordingly. And then see what you come up with. When you think you've got one drawn, turn to the people around you and see how yours looks compared to theirs.
Is this one the amount petition?
I don't think so. Is it? Let me see. No, this is on the 12th edition. Yeah, it's chapter 2. We're off a chapter number. I'll kind of get you started for those of you who haven't yet. Go ahead and keep continuing. If we're going to have so we've got the heat added on the bottom, or we could just call that heat or amount of energy added. And then on the y-axis, we've got temperature, change in temperature from minus 100 to 120. See if you can continue with that curve, and then look at those around you. Still see a little bit of writing, so I'll give you a couple more minutes. Good, this is looking pretty good. Where are the major important points here to note? Melting and boiling point. So that would be minus 53 for a melting point. It's about, I don't know, here. And boiling point is 97. We'll say that's about here. So those are the points at which we're going to add heat or add energy without changing temperature. So we're going to change temperature as we heat up the solid dibromomethane to its point. Then we add energy without changing temperature because that energy has to go into actually melting the solid. Now how long these lines are or what angle, how steep they are, that we don't know. That's other information that we don't have. So what's important is that it flattens out at each of these points. All right, how long you let it go straight, we don't know. We'll have to figure that out by looking at something else up. So now we've got our heating curve and we have a sense of what things are doing at each phase. What would you say is or not what would you say, but let's look at this particular line right here. Let's say we wanted to know how long that should be. It's not given in the problem. What number do we need? What's that number called that would tell us how long to be that line? It's a measurement of energy. What would that particular one be called? Do we know? This particular length of the heating curve, if we wanted to know how long that should be, how much energy that should take up, what kind of information will we need to know? Yeah, the heat of evaporation. So this amount of energy is the heat of vaporization or heat of evaporation, however you want to call that. That's what that length in energy space is. So here we've got our energy. The longer that is, the greater the heat of vaporization is. What about down here? What tells us this distance in energy, this amount of energy? What's that one called? What's that quantity called? It's another heat of something. Fusion? Heat of fusion or heat of melting. That's the amount of energy it takes to melt something.
So it doesn't really matter how long they are, I guess.
Well, not in this kind of a question because we're not given that information. If we were given those numbers, then we could have a specific x-axis and we could say, all right, it's 300 calories is the heat of vaporization. So goes from 100 to 400 or something. You know, we could figure that out if we had those numbers. Right. So then we can answer some of these other questions here. we talked about what happens in the curves. So what is the state of dibromomethane at minus 18? That's hard to see here. Minus 18, what would the state be?
Wouldn't it be a solid?
Liquid.
Well, so the question is minus 18 above or below the melting point? That's above the melting point because the melting point is minus 53. So if we're above the melting point, we're a liquid until 97 when we change into a gas. So here, remember here is solid in this part, liquid in this part, and vapor over here. So then what's the state of dibromomethane at 110? That's a gas. And today we're going to work on this part of the curve in lab with actual water. So you're going to heat water up, measure the change in temperature, and then come up with a curve. We're going to do it by time because we're not actually measuring the amount of energy put in, but should be the similar idea. And then finally, E, at what temperature will both solid and liquid be present? Yeah, negative 53, right at the melting point. That's what the melting point tells us. We'll have both states there. Both states exist there. Remember the other picture in our other example here? When both states are coexisting, that's in the middle of boiling or melting. All right, good. Okay, let's practice some conversions and some units because I know that's been an issue for some people in this chapter. And this will be something that we deal with up in lab as well. Let's talk about energy and food. The different parts of the food have different amounts of energy contained in them. What do you think is the highest energy storing component of a typical food? Kind of a weird question, I guess, but if you're eating, I don't know, what's something you like to eat?
Cake.
What? No, I said what do you like to eat? So let's say cake.
Yes.
All right, eggs. Eggs is probably good. Let's maybe not have so much cake. We'll pretend that we're healthy and we're eating some eggs. So you've got various components inside that egg, right? You got water, certainly. You've got protein. You've got fat. You've got carbohydrates, sugars. What do you think gives you the most energy in that? Protein? Carbohydrates? Okay. Yeah. Well, everyone is wrong.
Okay.
Sorry to say. Let me just check that to actually make sure that's correct.
Depends what terms. Okay? Carbs does give you energy, but
Yeah. So I guess maybe I phrased it wrong. I didn't mean what gives you the most energy. I meant what contains the most stored energy. Does that change your answer? All right. It's actually the fat is the most densely stored energy. And of course, different fats are different, but in general, fats average about, let me see if I can find it here, 9 kilocalories per gram. So every gram of fat contains about 9 kilocalories of energy. So when you eat a gram of fat, you're ingesting 9 kilocalories of stored energy. Now, if your body uses that, then it's burned and you feel that energy or whatever. But that's the actual stored energy in there. That also means that you can measure that. You can burn food, and then the energy given off by that burning food is the energy stored within there. So fat is 9 kilocalories per gram. Protein is 4 kilocalories per gram. And carbohydrates are 4 kilocalories per gram. Now, if we're talking about nutrition, there's all these other issues here, because depending on what form it's in, whether it's very available, whether it's needs to be more digested to access things. So we're talking about just these raw ingredients, the chemicals that make up these things. What is the stored energy inside within them? And you'll work in lab today at looking at some nutritional labels and trying to calculate the total calorie. Remember, and this is one of those weird conversions that we talked about, that 1 kcal or 1 kilocalorie is 1 big C calorie that we see on a nutritional. And it's confusing, so make a little note of it to yourself that even though that says calorie, we're actually talking about kilocalories because of the capital C. And we're actually hearing about 1,000 of the little c calories. Okay. Now let's do an example. Let's say we have some kind of food that we find out has 37 grams of carbohydrates, 19 grams of fat, and 23 grams of protein. What is the total energy in the food? Now, how do we figure that out? What do you think? Yeah, it's kind of a convert. We want to take our grams and turn them into kilocalories. It's not really a conversion because it's not the same type of unit, but we can say we have 37 grams of carbs, and we know that each 1 gram gives us 4 kilocalories of energy, so we can multiply those and get our total energy. So that's going to be 37 grams of carbs times 4 kilocalories per gram. And that gives us 150 kilocalories. And we can do the same for the others. Let's keep our numbers here. Okay. 19 grams fat times 9. 170. And then if we're running a little bit here too, and then 23. It's going to be 90. And then we can add all those together. And get 410 kilocalories total in the food. And that should be the same as the calories listed on the label per serving. But sometimes not, and you can check that, and we'll see that today in lab also. So let's practice a little bit of a conversion. If there is, this is our conversion factor, 4.184 joules in a calorie. How many kilojoules are in these 410 kilocalories. So we've got 410 kilocalories in this food. Let's say we want to convert that to kilojoules. How do we convert kilocalories to kilojoules using that? See if you can set that up and work through it. All right, so what kind of numbers are you getting for this one? We'll look at some numbers first, and then we'll come back and go through it. Anybody get a number?
1,715.44 joules.
Okay. Anybody get anything different? Almost there? Okay, give me another couple minutes. 1715,
1,000.
1715 kilojoules.
Yeah, that's what I got too.
That's what you got?
Yeah.
Did we get anything different? All the same? All right. How did you get this? How'd you set it up?
To get the conversion, because you already gave us that conversion. But
Okay.
we don't know about, like you told me to, we should have. It's 1 kilojoules equals 1,000 joules. So first you converted the calories into joules, and then the joules into kilojoules. That's good.
Okay, so we've got kilocalories, right? So one way we could do this,
So kilocalories into calories.
kilocalories into calories, so that's going to be, and we'll talk about a little bit of a shortcut here too, but for those of you who are about to say I'm doing something wrong. So we're going to go kilocalories into calories, and then use our conversion to get calories to joules.
And that's low calories, so lowercase.
Right, lowercase. Yeah, it's especially bad because calorie, yeah, the C is, right. Right. So unless we're looking at food in this class, we're going to always use lowercase cals and kcals so we don't get confused. And then finally we need to go joules to kilojoules. So that means we're going to multiply by 1,000, 4.184, and then divide by 1,000. Get about 1715 kilojoules. All right, so what did we do that is a little extra here that wasn't exactly necessary? Right now? What's wrong with the first step? The first and the last step? Why? Yeah, so if you notice here, we multiply by 1,000 and then we divide by 1,000. So if you multiply by something and then divide by something, that's just like 1, right? Why is that here? So how could we have avoided that? How might we have noticed that that was going to just cancel itself out? Any idea?
In the question itself.
How?
Take that back.
I know you're right, actually, but
I can't explain.
Okay.
But see, if you don't, like, it's kind of, it's still, you know what I mean? If you don't, if it's not good at.
yeah, I mean, look, if this works for you, if this is how you set it up, great, set it up like that. But one thing you might notice is that the question is talking about kilojoules in a kilocalorie. So we've got 1,000 of each. And the conversion gives us calorie and joule. So it's sort of like we're multiplying each of these by 1,000, which is really the same relationship. So if you see two units with the same metric prefix, whether it's kilo or milli or whatever, if both units you want to convert between have the same prefix, you don't need the extra thousands in there because you're just going to end up undoing whatever you do.
So it's a short
To just use this conversion, to just say that 1 cal equals 4.184 joules is the same as saying that 1 kilocalorie is 4.184 kilojoules. You can always put the same prefix on both sides. You see? So you can always put the same prefix on both sides if that helps you in a problem. Now, if you don't want to mess with that, you can just do it this way. That's fine.
That's what I go. So when we're multiplying it, we do just like.
So the other way you could do this then, I guess let's just write it out here. You could go 410 kilocalories and you get the same answer.
Yeah, I get it. But if you don't know the new conversion, it's kind of.
Yeah, and then to make yourself have an error, but you can recognize that always have the same prefix on both sides and still maintain the same conversion. All right. Okay, did we look last time? Let me jump back up here a second. We looked at temperature. We didn't look at specific heat and heat capacity, so let's do that. I don't think, did we? Oh, we did talk about this, okay. So remember that it takes 1 calorie to raise 1 gram of water. That's how that calorie is defined.
And then that's the upper calorie? Or just
Lowercase calorie. Lowercase calorie. 1 for 1. No, I'm not seeing this thing. Oh, here we go. Okay, that is called the specific heat. Depending on the material, that might be different. Other materials might require more or less energy to raise a particular amount. So we actually have a number for dealing with this, and it looks like this. We'll call it SH, specific heat, for water, is 1 calorie per gram degree C, which is the unit way or the math way of showing what we just said in that sentence. It takes 1 calorie per gram per degrees C. Right. The only reason we write it this way now is because I want to give you some other numbers and we can compare those and talk about what that means. So first of all, we can convert this. So we can say 4.184 joules per gram degree C is the specific heat of water. But let's look at some other compounds, some other things that we may have experienced. Aluminum. Does everybody know what aluminum is? It's like a silvery light metal. Yeah. So the specific heat of aluminum, I'm not going to tell you the number first. I'm going to ask you to think about it. Have you ever experienced heating aluminum? How might you have experienced heating aluminum?
Throwing a pop can in a fire.
Throwing a pop can in a fire. Okay.
soldering.
Soldering with aluminum?
Yeah, it's
Okay. Oh yeah, because you worked on airplanes, right? Jets, yeah.
I feel like make a baked potato and wrap it in aluminum foil.
Yeah, okay, so you wrap a baked potato in aluminum foil, or really any hot food, and you put it in aluminum foil. What happens? Would you say that aluminum foil gets hot more or less easily than water? Do you think it takes more or less energy to heat up aluminum to the same temperature? Less. Right, absolutely. So that means that its specific heat is going to be lower, and it's actually quite a bit lower. .214 calories per gram degree C. So that means it takes only about a fifth of the energy that it takes to heat up water to a certain temperature to heat up aluminum to that temperature. And that's our experience. So if you take aluminum foil and you put it over something hot, it gets hot almost immediately. Right? And then actually it cools off because it dissipates the heat. But it gets hot almost immediately. If you put water on something hot, you're actually going to cool that thing off before the water starts to heat up. And really, water has one of the highest heat or highest specific heats of any common material. Pretty much everything has a lower specific heat than water. What does that tell us about? Another question. What does that tell us about the steepness of these inclines on a heating curve? So the steepness of the incline relates to the heat capacity or the specific heat. So if this is water, do you think that something with a lower specific heat like aluminum would have a sharper or shallower curve when you're heating it up? Sharper, because for less energy you're going higher up in temperature. And so that's how we could find this information if we wanted to know those specific slopes. You can even see with water that there's a difference. So look at, and they don't really talk about this in this part, but look at the two slopes between ice heating up and water heating up. So does that mean that ice or water has a higher specific heat? Water?
Yeah.
Why? Yeah. Because you can see this line is not quite as steep as this one, right? That means that it takes more energy to heat up water the same amount of degrees as to heat up ice. And in fact, the specific heat of ice is about 0.5, so it's only half of what liquid water is. So it's much easier to heat up ice. It takes less energy to heat up ice per degree than per water. So that's specific heat. The other thing that's nice about specific heat is if we know something's specific heat, we can calculate the amount of energy used to change the temperature of a sample. And this is something that you'll be doing in lab today. So if we know it takes 1 calorie to raise 1 gram of water, 1 degree C, what if we have 100 grams of water, and we heat it from, let's say, 25 degrees C to 65 degrees C. How much energy was used to heat that water, that 100 grams of water, from 25 degrees to 65 degrees? Any idea how you might figure this out?
First, you find the difference of 65 and 25.
Yeah, we need to find the difference in temperature. And the difference in temperature we often denote with a triangle. Triangle means difference. Oh, it's a Greek letter delta, but we can call it a triangle. Difference in temperature. And that's the difference, the temperature change. In this case is 40 degrees, right? Going from 25 to 65 is a difference of 40 degrees. So now let's take a look at this unit for a specific heat of water. 1 calorie per gram degree C. We can kind of set something up here to cancel out that gram and that degree C and end up with energy. If it's 1 calorie per gram degree C, and we actually have 100 grams, then we've got 100 calories first, right? So that calorie is that cancels grams. But now we don't just have 1 degree C, we have 40. So we multiply by the change in temperature, 40. And that tells us that overall, it takes 400 calories to heat 100 grams of water from 25 to 65. Right, so grams cancel, degrees C cancel, and we're left with calories.
Wait, how did you cancel the degrees?
With the change in temperature, the number of degrees.
Oh.
So this is the calories per each degree, and if we went 40 degrees, we have to multiply by 40. The overall equation, if you want to think about it that way, is that the total heat is going to be the mass of whatever's getting heated, so water in this case, yeah.
So it's 100 times 40?
Right, so that's 4,000. Yes, thank you. Sorry about that. Yes, 4,000 calories. So anyway, going back to this, heat is going to be the mass of whatever's heated, so that's the 100 grams, times the change in temperature, how much you heated it, and then times the specific heat. Now this is almost always done for water. We care mostly about heating up water. The reason for that is that even when we're measuring other things, we measure them by sticking them in water and looking at the change in the water temperature. So usually that specific heat is going to be 1, and we're not going to have to worry about it. So we measure the mass of whatever's changing times the change in that. The change. And you'll get to do some of that today. All right. So that's pretty much all the basic material from this chapter. What do you want to work on now for the last little bit? We'll do a couple examples. What's been giving you the most trouble looking at this stuff?
I was having a problem with number 7 with the map.
Number 7 in the tab? Okay, let's look at that. So we have it. All right, an empty beaker. Draw a picture here. Weighs 45.897 grams. We stick some ice into it. And now it is 68.034 grams. The ice was poured into another container. So we pour the ice out, leaving another empty beaker, but it's got some drops of water on it. It's not perfectly empty. And that is now 46.146 grams. How much ice was poured into the other container? And how much ice was originally weighed out?
Subtract first, and then after that.
Yeah, so more specifically, what would you subtract for which?
Are you going to subtract the beaker with the ice, crushed ice, and the beaker are originally weighed empty?
Okay, so this, we'll call these A, B, and C. So B minus A is going to be the total ice that was weighed out. Because you have your mass of your empty beaker, and whatever you put in there, that's the extra, all the extra mass. But then you dumped it into another container, so we need another term to actually see how much was in the new container. So let's call our new container, here's the thing we dumped the ice into. And we want to know how much ice actually got into there. How do we figure that out? What? That's what we want to know. What's the mass of the ice in this new container? C minus A? C minus A will tell us how much liquid is left in the beaker, in the original beaker. So we could use that with this. But there's a little bit easier way to do it. Right. How much ice is in the new container that you dumped it into? Right. B minus C is the actual ice that made it into the new container. And the reason we do it that way is because often that new container, it's not practical to weigh it. Maybe it's a big thing, and we want to know how much got in there. We can't just take the number that we weighed out initially because we know we left some water behind, and that's going to mess up the calculations. So we need to dump it out and then weigh our empty thing that we dumped out of, the residue left in it. Right, and then whatever's left, no, whatever's left you subtract because that didn't make it into the wherever you're putting the stuff into. This also works with solids. So let's say you're going to measure out, some amount of a solid. You need to measure it really precisely. So you take the jar and you take your balance and you put a weigh boat on the balance, and you start measuring out. You weigh the weigh boat and then you measure out whatever, 5 grams. Then you take your weigh boat and you put it into your reaction mixture. But even if you do a really good job, there's still going to be some left on the weigh boat, right? There's a little dust or a little trace of something. So if you really want to be precise about how much you put into your reaction, you have to weigh the weigh boat again and then subtract that little bit that's still left. So use that empty weigh boat that's not totally empty as your 0 instead of the first truly empty weigh boat mass. Does that make sense? Kind of? So you're accounting for that. With something like a salad, we don't usually do that unless we're really trying to do some analytical chemistry that we need every single little thing accounted for. When we're making stuff in lab and we're doing reactions, we don't usually care. The reason we care about this one that you'll do today is because water leaves a lot of residue behind, or ice does. When you weigh out ice in a beaker, by the time you've weighed it out and you pour it, there's a decent amount left that is really going to mess up the calculation, so we have to account for it. That's how we do it.
So you're just subtracting it from whatever empty capacity makes.
Yeah, so this is really the number that you want. This is the important number. How much ice actually made it into that container. So the original is just so you have a sense of how much you're putting in. This is what you actually want to know to do the calculation. How much ice actually made it into the container. In this, yeah.
So wouldn't you would take B and subtract A, and then you'd subtract C. Don't you have to get the weight of the other beakers?
The beaker's on that one too, right? If you took C minus A, that would be the leftover water, and you could subtract that from what you got in B minus A, but you could just do this. So that's called weighing by difference. All right, other questions or things you want to talk about? Thanks for bringing that up. No? Everybody's good?
Regarding the energy room,
Yeah.
Because in some parts of the book I felt like it said that the energy was being released.
All right, you want to talk about release versus absorbed?
Yeah.
Endothermic versus exothermic? Okay, let's talk about that.
Some parts like, oh, I'm totally good. Like, yeah, it is releasing energy. But some of it seems like it.
Yeah. There's one good way that I like to keep this straight. So I'll tell you that, and maybe it'll help. I don't know. So we've got exothermic versus endothermic. Exothermic means heat is released to the surroundings. Endothermic means heat is absorbed. So what physically does it look like or feel like when there's something exothermic going on in your reaction? How would you know that something exothermic is going on in the reaction? Well, hopefully not. Maybe. If you have an exothermic process, what should happen to the temperature? Yeah, it should go up. So exothermic things get hot. So exothermic gets hot.
You see, that's tricky because even things at a solid state is hot. But you talk about the environment as well?
Right. So when we say gets hot, what we're really meaning is
The environment, okay. I just want to make sure.
the environment gets hot. The actual thing that's in the reaction is getting colder because it's giving off the heat. Right? So the environment, we should clarify that, or what we would call the surroundings. Surroundings get hot. So you do a chemical reaction, and it heats up, and you touch it, and you go, oh, that's hot. That's an exothermic reaction. So then what happens in an endothermic reaction?
but not the.
Yeah, but so then how do you, what would it feel like to you? Yeah, so in an endothermic process, the surroundings get cold. It's drawing heat from the surroundings into the wherever, and so the surroundings feel colder. Whether that's your skin touching the side or, so if you do a reaction in a test tube, it's endothermic. It's pulling in heat from the solvent. It's pulling in heat from the test tube itself, from the air around it. So all that is going to feel a little bit colder, and that's going to be with a thermometer.
But the thing itself, like for example, like if the thing turns into solid, like it's,
Right.
it's absorbing heat then. It's not like affecting it.
Right, so this gets a little tricky when we talk about things like phase changes. So let's think ice melting. We think about ice melting when it gets hot, right? It gets warmer, the ice melts. So then ice melting must be an exothermic process. But that's actually wrong. Ice melting is an endothermic process. It takes in energy. It requires energy to make that thing melt.
Right.
And so that's when it gets tricky. You have to think about what is actually happening with the energy going in or out of that particular thing, not what is happening in the room.
See, that's what's
Otherwise.
confusing me because so then would we consider even a phase change as a liquid to a solid? Kind of similar to.
Yeah, so let's think about that. Liquid going to solid, like ice freezing or water freezing, okay? Is that giving off energy or is that taking energy in to do that? It's giving off energy because it's now in a solid state. And those phase changes is where this gets confusing. In a reaction, it makes. But what that means is, and this isn't really detectable necessarily, but when water freezes, it actually gives off heat. And that's maybe weird, but it does. That's why that's part of the reason why your freezer has to keep cooling it. It has to transfer the heat to the outside because things freeze and they give off heat. One example of where this is used is if you make ice cream. Have you ever made ice cream with the old crank thing that you know what I'm talking about? There's this big crank thing. It's a big barrel, and you put the ice cream mix in the middle, and then what do you put around the outside? Salt and ice. So what does that do? What happens to ice if you put salt in it? It starts to melt. So melting is an endothermic process because it takes in heat. It requires heat. That ice, what you're doing is you're sucking heat out of the ice cream mixture, which freezes it quickly, which is why you do that. So you're freezing the ice cream mixture very quickly by sucking the heat out from the melting ice is sucking the heat out of that ice cream mixture. That's what those do.
So I'm just gonna not repeat myself as you're done, but so like some sort of an explosion would be endothermic? No, it would be exothermic because it's taking. Explain.
Because it's releasing.
Well, yeah. So a couple of things here. First of all, an explosion is actually a formation of gas. It actually doesn't have anything. Explosion means that you've produced a lot of gas really fast, and it doesn't have a container anymore, and so it blows apart. Heat actually doesn't have anything to do with that. However, most explosions give off a lot of heat. So you talk about something like burning. Let's just talk about burning something, like burning a fuel. Right? You burn some gasoline or something. That's an exothermic reaction. You're giving off heat. But you had to light it to get started, right? So if you think about the lighting, it seems like you're putting in heat. Actually, not the reaction. We'll get into this later, but that's something called activation energy. A lot of processes need a little bit of energy to get started, but the actual process then gets going and then does whatever it does. So that's maybe where the explosion is confusing because you have to light it to get it to go, but actually the process itself is giving off heat usually. So I guess this kind of shorthand works well for reactions, and then I would say if you keep in your mind that phase changes are a little bit trickier and you think about them a little bit differently, that might help. Because when you think about ice, if you think about does ice melting require energy put in? Well, yes, because you have to heat ice up to melt. So that tells you that that must be an endothermic process because you have to heat it up to get it to melt. All right, well, let's stop there. We'll head up to lab and make sure you finish your pre-lab and get that ready. Everybody's dressed appropriately for lab today. It's a pretty reasonable lab. Just keep an eye on what you're going to be doing. And I think you'll be fine.